Building a monocopter or any type of drone from scratch is extremely difficult. I've already gone through a couple iterations with this monocopter and they haven't even left the ground. Other people have been really successful with their monocopters and they clearly have a lot more knowledge on drone design and controls than I do. Unfortunately, I'm a lot less skilled, and so this has been a pretty long and painful process, but I'm happy to report that the monocopter is somewhat flying. And so I want this video to be a resource for people starting off on similar projects who have limited RC and programming experience. If you're getting stuck with something as simple as using a gyro or making something light enough to fly, then this video could probably save you a lot of time. I'm going to go over the monocopter in 4 broad areas: dynamics, design, filtering, and fabrication. And hopefully you can either learn something or tell me where I went wrong, or both. If you're designing your own monocopter, then use a counter-rotating system. This kind of sums up this whole section, but I know it's possible without one, and I have made non-zero progress toward understanding how, so that's what I'll talk about. I've been playing around with thrust vectoring vanes and gimbals for a bit now, and because I'm using a single ducted fan, the system experiences massive torque due to the angular momentum of the rotating EDF. This phenomenon is called gyroscopic precession, and it's visualized very clearly using the string test, where I hear whatever I'm using by a single string to observe rotation. When it comes to the monocopter I've been working on, the gyroscopic effect is so strong that if it's not accounted for, you simply can't take off. My goal for this version was to limit the precession to the point where I could at least take off. The control in this scenario is achieved by angling 2 opposite-facing servos in opposite directions. When I first ran the string test, it wasn't looking like it was working, but after some basic tuning, I actually got this to work pretty well. Hopefully you can see how the servos extend farther as I increase the motor RPM. I had a difficult time both constructing the PID and also getting good angle measurements from the MPU in the first place, but I'll talk about that in the filtering section. I was really happy when I saw these servos responding correctly. This was a big deal because without yaw control, again, my previous designs couldn't even get off the ground and would very quickly and clearly fail the spin test with barely any throttle applied. So at this point, I decided to send it. I printed these stands that attach the servo and hopefully give me enough ground clearance. I did need additional tuning because at first I was having the same takeoff problems as before, but eventually it took off. There's pretty much zero control authority here, but I was happy to mitigate the spin at least enough to get off the ground. You can see the monocopter is still rotating in air. Ballistic missiles are known to do this, but this is actually purposely induced to increase stability and accuracy, which means they have the opposite problem as me. Since I need precise control of the monocopter at all times, I can't use the spin to my advantage. This design has shifted from jerry-rigging everything to the side of the fan to putting it on top in a much cleaner fashion. Here's an exploded CAD view. It's made of 5 parts where the lower section houses the ESC and receiver, the plates hold the flight controller stack down, and the top section secures the battery. I printed the bridge out of PLA Plus because it obviously needs to be sturdy, and cut holes in the bottom to save weight. Using this design essentially guarantees that the monocopter is balanced across the roll and pitch axis. This was definitely not the case before. It also makes construction less complex. It makes the drone look a lot better aesthetically. There are some drawbacks though. A big worry of mine has been blocking the EDF intake airstream, and this design is the biggest offender thus far. I've staged a head about 50 millimeters away from the fan and shaped it somewhat aerodynamically to allow for a smooth air pull, but we already know that the EDF is well under its max thrust output by now. Stability-wise, it's an iffy and controversial design. Traditionally, a higher center of gravity ensures static stability in something like a rocket. It induces a pendulum effect that creates restoring moments. However, in a thrust-dominated system, this effect is either negligible or even harmful in the response of the monocopter because we have thrust vectoring. In addition, the high moment of inertia with respect to the motor means that the gyroscopic effect is worsened as the center of gravity moves upward, and since the precession is the main enemy of stability at this point, this is probably not the best thing for the monocopter. So a big message of this video and the channel as a whole is that anyone can build drones. That's why I'm really happy to be partnered with PCBWay. PCBWay is a PCB and part manufacturer that can bring to life almost anything you can design at home. I've personally used their services to make parts in advanced materials such as nylon, which I would have no way of doing otherwise, and they're an extremely reliable and communicative team. Ordering a plastic, metal, or PCB component is as easy as uploading your file to the website, customizing your part exactly how you want it, and waiting to get approved. So if you want anything from a simple PLA part to a complex PCB to some funky geometry machine in metal, you should definitely check out PCBWay. Thank you so much to the PCBWay team for continuing to support this channel. So before this, I thought that if I had a basic understanding of PID logic and could map numbers to servos in C++, then I could build a rudimentary control system. It turns out the thing I got stuck on was actually getting accurate angles from the gyroscope in the first place. I'm using a Long Flight Dream as my flight controller, which uses a TNT 4.0 and an inbuilt MPU 6050. I've been working with these guys at Long Flight for a bit now, and they're awesome people with a really accessible product. The MPU 6050 is probably the most widely used hobbyist gyro, but you do need a good filter setup if you want to use it in an active control loop. So to break it down very quickly, the big enemies of good sensor data is noise and drift. Something like an MPU gives both dynamic gyroscopic data, which moves in time but drifts, and static accelerometer data, which are absolute quantities. You want a term like the alpha one I have here to weigh how much the gyroscopic data is used with respect to the accelerometer data. If you tune well enough, you can end up with some non-drifting, fast-responding X and Y, or in this case, roll and pitch angles. Unfortunately, since we're building drones, it can't stop here. Unlike pitch and roll, yaw can't use accelerometer data because there's no inherent correction mechanism in the MPU 6050. As is, our yaw value drifts significantly, and since we're especially sensitive to yaw because of the gyroscopic precession, this is obviously a massive issue for us. Your options now would be to either get a magnetometer that uses the true north as its correction mechanism, or implement another filter to stabilize the yaw. I used a magic filter that estimates and optimizes yaw drift based on the expected gravity vector. Luckily, there's a ton of Arduino libraries with Magic algorithms, so all I have to do is give my MPU readings and a filter parameter, which I name beta in my code. Side note, you do have to tune this similarly to the complementary alpha parameter, and when I give this, it just spits out a yaw angle. Applying these angles to your PID loops is pretty easy to get started, and I'm not going to go into that just because I'm not really qualified to talk about that. I'm also not qualified to talk about the filters, but my point is that it's usually not a plug and play thing when it comes to these MPU kind of hobbyist level gyros. For propulsion, I use a single 64mm EDF with the 4S LiPo. It's a heavy setup. The EDF is rated at about 1250 grams max thrust, and we're already at 250 grams. With the ESC and FlySky receiver, this brings us to well over 300, about a quarter of max thrust. Again, assuming that we have max thrust in the first place, which is not the case. This is where lightweight PLA comes in, and this thing is a total game changer. For the longest time, I've stayed away from lightweight PLA. With my drones in the past, I always somehow estimated how heavy my frames would turn out, even at 0% infill. I heard that lightweight PLA was tricky to print well, and I was honestly too lazy to spend time tuning my printers. However, I'm happy to report that it's actually very simple and 100% worth it if you want to do anything aerial. I got non-foaming lightweight PLA, which means you don't have to touch flow rates or layer heights because it prints very similar to regular plastics. It's obviously a little weaker than the PLA Plus I was using, but if this monocopter crashes, it's going to break anyway. And this prints so well, somehow there are no layer lines and I've never had to post-process. The nose cone weighs 30 grams. I'm going to slice this with my regular PLA and you can see that it weighs 46 grams, so the weight savings are pretty significant. Anyways, that's enough about the lightweight PLA. My main point for this section is don't be an idiot like me and not use it. 4 MG90S microservos are used in the back to vector thrusts using the thrust vanes, which are inserted through the EDF frame to preserve the unibody construction. Before, I was gluing them to little attachments in the back, so this is a massive improvement. To put everything together, I use a 3D printing pen. You will have to use the same filament in this pen if you want to bind pieces together. In my experience, you can't use lightweight PLA to combine two PLA Plus parts, for example. In classic engineering fashion, I made this monocopter very inaccessible, and so I had to cut these really big and nasty looking slots in order to reach things like the battery or the flight controller. So where does that leave the project? My goal is to streamline this design. I'm happy with the overall concept. I think I can cut a lot of weight down, especially in the nose, and kind of refresh the body, make it a little thinner. But like I mentioned before, it's 100% time to start at least considering a counter-rotating system. Thank you guys so much for the helpful comments and messages. Thank you for watching the video and supporting the channel. I hope this video will help people in the same boat as me, people who want to mess around with drones but don't really know where to start. But I'll see you guys in the next update.